She has been visiting us for a few days, and I thank her very much for being here physically. It has been a long plan visit, so we managed. And she graduated and got a PhD in Queen's University in Australia, and then she moved to Europe first as a postdoc at the Max Planck Institute in Heidelberg, working with Eva Schiller, and then she moved to France at the Institute of Astrophysics and Planétologie in Toulouse, where she got a postdoc first, and now she's an astronomer. And her main, she mainly studies nearby galaxies, and she's part of many collaborations which aim to cover the nearby galaxy centers with all possible frequencies. And she's in the PHANGS collaboration, which is an amazing survey of many nearby galaxies, and she's co-PI of the large program, ALMA large program, which has been observed recently, and the data have been published last year or more than a year ago. And so today she will talk about the results that they got from ALMA data. Thank you.
Thank you very much, Rosita, and thank you for hosting me here. So today I'm going to be talking about PHANGS, which stands for the physics at high angular resolution in nearby galaxies. And it's an international collaboration to study the physics of cold gas, star formation and feedback in the local galaxy population. So as the usual disclaimer, as time goes on, we do less and less of our own research. We do more and more teaching and administration. So many of the results that I will be showing today are of postdocs and of students in the team who've done a fantastic job. Okay, so to first order, what I'd like to talk about today is how molecular gas, molecular clouds, and the star formation that happens inside them is sort of coupled to the properties of the host galaxy, both the global galaxy properties and the local environment in which the molecular cloud exists. So, I think sort of it's pretty much standard textbook knowledge that star formation always happens in a molecular cloud. And I would say the picture that emerges from PHANGS is that it's really the galactic disk that in a sense, regulates and sets the properties of the molecular cloud. And so the galactic disk is, in fact, the context for the star formation that's happening within them. So all of the sort of small scale processes that we are familiar with when we talk about star formation, turbulence, radiation, and self-gravity, all of that, in a sense, the galactic disk sets the boundary conditions for those small-scale physics, microphysics of star formation. And the other thing to remember, of course, is that star formation and stellar feedback is also important for the evolution of galaxies, and that this sort of life cycling between molecular clouds and star formation that's occurring in the galactic disk itself is really important for the secular growth of galaxies and the formation of the stellar populations, for the chemical enrichment of the ISM, and also for driving material up into the galactic halo and the circumgalactic medium. So I expected there to be lots of students, so I just thought I'd just quickly sort of set the context in terms of what galaxies in the local universe looks like. So for galaxies that are sort of normal galaxies in the local universe, it's the stars that dominate their gravitational potential. The molecular gas that dominates the mass is the ISM, but not the volume. So the volume is basically filled by atomic and ionized gas. And that molecular gas, which is what we study with PHANGS ALMA, itself is highly structured, and it covers ranges of densities between a few hundred to 10 to the 6 particles per centimetre cubed, and it's really in that really highest density regime where you can have the emission not only from CO but also sort of more exotic species. That's the cause in which the star formation happens. Okay, and of course once those stars form, they immediately exert feedback, and there's various different types of feedback processes. Photoionization, radiation pressure, supernovae that go off, stellar winds. And it's sort of an open question as to which of those dominates? Do they dominate? Do the processes have a different importance in different galactic environments? And these are part of the questions that we're trying to answer with PHANGS. But I mean, one of the things that is important to say is that the characteristic timescale of many of these sort of microphysics of the ISM processes are sort of mega years or tens of mega years. And these are much, much shorter than the timescales of galactic evolution. So when we're studying galactic disks at high resolution, we're sort of accessing this sort of quasi-equilibrium state. And so the types of questions we can ask is sort of, how does this quasi-equilibrium, how does this sort of cycle exist and persist so the galactic disk doesn't collapse in on itself? How does that emerge? Do the various terms change depending on where you are in different galaxies, and what are the sort of key timescales and efficiencies of those processes? So that's sort of the theoretician's way of thinking about things. I'm an observer. So this is my sort of observer's way of posing those questions, which is, where is the cold gas in galaxies? What is its dynamical state? And what sets that state? And in terms of the star formation, where does the star formation happen really? Where do we see it happening with relation to galactic structure or to the cold gas distribution? How efficient is it and how long does it take? So I feel like this was yesterday, but this is sort of the state of the art sort of now 10 or 15 years ago. But just to sort of really sort of focus your attention on the revolution that ALMA has made. In sort of 2008, as I was sort of starting my PhD, this was sort of the gold standard of nearby galaxy surveys. It was the era of things and Heracles, which were surveying nearby galaxies, populations of about 30 galaxies with kiloparsec scale resolution. And this was completely state of the art. And these surveys were really fantastic, and they taught us a lot about how the cold gas in galaxies is related to galactic structure, the phase balance in the ISM, and sort of, you could sort of pick out the arms and the centers of galaxies. But what we couldn't answer with those types of surveys is, what are the properties at the scale that's most relevant for star formation? So on 100 parsec scales, what is it? Is the gas self-gravitating? And what's happening at the scales, in fact, where most star formation theory, in fact, sort of tells you or makes predictions about what is the most important physical parameter. Is it density? Is it Mach number? Is it the virialization of the cloud? And so PHANGS was sort of conceived to really try and test some of these cloud scale star formation models in the context of the local galaxy population. So the idea is what we really needed when we sort of started thinking about the survey was a quantitative description of the cold gas at 100 parsec scales or better if possible, but across a representative sample of galactic environments where star formation is happening in the local universe. So that sort of brings us to the design of the PHANGS ALMA survey. So basically we selected, so in total there's about 100 galaxies that are sort of part of PHANGS ALMA, or 90, some of which are directly observed in the large program, and some of which we have taken from the archive because they're very similar observations to what's in our program and suitable targets. And we select galaxies that lie on what was called the star forming name sequence. So that's this sort of region of stellar mass, star formation rate space. So the plot here shows in blue dots all the galaxies that we've observed with PHANGS ALMA. The red is the targets, the subsample of targets, which we also have PHANGS MUSE observations, and in the black squares, it's where we have also observations from the HST. So in terms of what I'm going to show later, it's important to keep in mind that we deliberately selected galaxies on the star forming name sequence. We don't target starbursts or anemic weakly star forming galaxies. We chose them to be relatively, well, we avoided completely edge-on galaxies, and of course they have to be visible from ALMA, and closer than 17 megaparsecs, which means that sort of a fiducial angular resolution of ALMA of about 1 arcseconds will access 100 parsecs. And you could ask, oh, why would you target that main sequence? There are closer galaxies in the local group where you could get much, much better resolution. And the answer is that, if you really want to characterize star formation at redshift 0, you should target the types of systems where most of the star formation is occurring. So while it's true that you can get better resolution in small, lower mass galaxies by looking at the local group, they don't necessarily tell you about star formation as it happens in a representative way at our epoch. So that's just a quick slide of those 74 galaxies that we observed with ALMA. Essentially, you can see here that they do cover sort of a range of morphologies in terms of spirals and bars and central concentration. We essentially used a WISE-3 contour in order to decide where most of the star formation was happening, and the idea was to cover the full extent of the star forming disk in these galaxies. So this is well, on the right here I'm showing a sort of an extract from the CO Atlas of Galaxies that we published I think late last year as part of the public data release. So for each of the targets, if you go to the website, you can find the setup of the field, various maps derived from the ALMA CO emission, including the velocity information. We have that for all of the targets that we have observed and processed out of the archive. And on the left, I'm just showing some of the statistics for people that are interested in observing with ALMA. I forget since this is an ARC node, people might be interested in this kind of things. So the total area that we mapped is sort of over 10,000 square kiloparsecs, and you can sort of plot basically shows the area mapped as a function of the distance of the galaxy. So it's not of course exactly the same area in all galaxies, but we did try and sort of cover the star forming disk in all of our systems. And then you can see that for some of these very nearby systems, when you use the 12 metre, we had an extension which only used the 7 metre and the total power array. What else? Oh, yeah, I should say the obvious thing, we observed the CO2 to 1. Just because that's the most efficient tracer of the bulk of the molecular gas. It doesn't really necessarily access the really densely star forming gas, but in terms of charting the reservoir of the molecular gas, that's what we were after. And your sort of point source mass sensitivity means that, well, depending on the galaxy, we're sort of looking at 10 to the 5 solar masses in terms of our sensitivity, our typical sensitivity, a well-detected molecular cloud, which is sort of on the large side compared to what the canonical GMC is considered to be in the Milky Way. And then just on the bottom, I showed this later as well. Today, if you want to, you can go to our website and you can download all of the cubes. You can download any moment map you like at a multiple suite of resolution, including error maps. We also released a table which had sort of homogeneous galaxy properties. So one of the things you quickly realise in nearby galaxy studies is that everybody has a different favourite distance. So we re-derived all of the galaxy properties using homogeneous criteria and calibrations for all of the properties. And we also released that along with our data processing pipeline. And I'm responsible for making the cloud colors, and they haven't been released yet, but the aim is to have them out by the end of the year. So that then is just a snapshot of the peak brightness of the 2 to 1 line across many of our targets, and a bit of a zoom in, just really just so that you can appreciate, like, everything that you can see on these maps is a significant distinction, and you can spend hours just staring at the maps and being amazed by how much more like lace work some of the galaxies are. So I won't have time to talk about the other sort of observing programs today, but just so you keep in mind, PHANGS is not just the ALMA survey, it's actually sort of an international collaboration that tries to study also feedback and star formation across the spectrum. And in particular, there's, of our 90 galaxies, 38 of them have been observed with JWST and 19 of them have been observed with MUSE, and those same 19 will be observed with the JWST, with the same sort of field of view across all those targets. There's sort of smaller programs to try and catch as much of these galaxies in the H1, quite hard work, and also narrowband H-alpha imaging surveys. Sort of, at the start, we thought we could get by with Recherche narrowband H-alpha imaging, and in the end, we decided it was just too much hard work, and it was easier to go back and re-observe a lot of them. reobserve them homogeneously, is what I like to say. So that's, this is just to flash a few images of what the MUSE and HST data looks like. Again, these are all publicly released now, so you can go and get them from our website as well. So the MUSE, you can access maps for the main stellar continuum bands across the MUSE observing range, and you also have emission line maps that are in the part of the public release for the main emission lines that are across in that MUSE wavelength range. And then in terms of, I'm not sure if there's a big optical eye view community here, but just to sort of situate where the PHANGS MUSE stands in relation to some of the other optical eye view surveys in the nearby universe. We're at this 100 parsec spatial resolution, and in terms of the sort of spatial coverage across nearby galaxies, it's extremely good. And for HST, so this is sort of UV to optical imaging across 38 of the galaxies, some composite maps, including part of the public data release there includes sort of catalogues of associations and clusters, and I'm not sure if it's out yet, but it will soon be out if it's not out. That the positions of all those clusters is out, and the sort of properties in terms of their age and their mass is also part of the public data release in all of these galaxies. And then that's just to situate PHANGS HST in the context of sort of other HST work. So you can see that the good survey targets are sort of these sort of much more highly star-forming massive systems. So PHANGS here is orange, the PHANGS HST, I've lost my pointer. And LEGAS, which is another big HST legacy program, reaches much further down into the dwarf galaxy population than we do. Okay, so essentially PHANGS HST is what you can see in orange solid dots, and the crosses are those that also have MUSE data overplotted onto the sort of the typical M-star formation plane, where that sort of cloud of points is of course the star forming main sequence. All right, so just going to use a bit of time now to actually talk about some of our results. As simple as I try to be I'm an observer. I like simple things, so the results I'll talk about today are simple. You've got a question or? So I guess one of the first questions you could ask is, well, like, where is the molecular gas in nearby galaxies? So that was taken by the 30-meter telescope, and we can see that there are spiral arms, and once you have maps that look like this, you can actually do a much better job of allocating that CO emission into structures that you confidently say that's a spiral arm, that's a bar, that's a lens, that's a ring. And so one of the products that we've released is environmental masks for each of the PHANGS galaxies. So this is all being done in a sort of uniform way based on 3.6 micron imaging. There's a part that's been, the bulge in the disk is essentially characterized using a photometric decomposition with the bar, the arms, and in the cases where they exist, the sort of rings and lenses identified by eye by several members of our team to sort of make sure that they have self-consistent results. So those masks interest you, that they sort of, the fixed files look something like this, where there's a color code for each of these regions. Yeah, so they're all sort of visually or photometrically identified. There's no kinematic information that's being used to define these masks. That's something to keep in mind. And yeah, and so this is I think the simplest, but still it's, I think, a very interesting result, which is just say, okay, well, where is the CO emission in nearby galaxies? So if you look at on the left, this is the area covered by these different environments. So the centers are in red, bars in green, arms in blue, and then interarm regions and sort of disks that don't have any clear spiral structure in orange. And you can see that the vast majority of nearby galaxies, in terms of the area that they cover in the sky, are actually these sort of structureless parts of galaxies. But then when you look at the CO flux, where that's coming from, I've expressed it here in terms of mass, but our galaxies have such similar metallicities that, even with X-factor considerations, we don't, this doesn't change very much. Suddenly centers really punch above their weight. They contribute much, much more of the CO emission from galaxies. But I think as somebody who likes to study the sort of the boring outskirts of galaxies, I think it's still interesting that even once you consider by flux rather than area, sort of the inter-arms and outer distance galaxies are still responsible for nearly 50% of the CO emission in nearby galaxies. So, those are still the sort of most of the place where a lot of the star formation is happening, or with a lot of the molecular gases. So much for sort of the general distribution of the molecular gas. One of the questions we also asked ourselves is, what about if we concentrate on the peaks in the molecular distribution? So how are molecular clouds distributed in galaxies? So this is a project that's being led by a graduate student, Josh Machado, and to try and illustrate what he's been doing, because this is the background here is an ALMA map, and he essentially identifies the center or the peak of each of those clouds that we identify in that galaxy, and then he compares the clustering in two different ways of the observational data against a random or a reference distribution. So the two distributions that he's looked at is the top one's just the flat distribution, so completely not realistic, but it's essentially just randomly pop down points across the field of view. And another reference, the reference distribution, which is essentially an exponential disk, which is a much more physically motivated reference distribution, because most components of galaxies fall off with an exponential. So the two sort of measures that he's made is to look at the distance to the nearest neighbour, first, third, fifth nearest neighbour, and the data is in grey, and then these reference distributions are in blue and red, and you can see that the data, even compared to the sort of exponential disk distribution, is still much. The distance to the nearest neighbour is smaller, and it's a much more clustered histogram, or a tighter, narrower histogram than what you would expect from just an exponential distribution. And then a similar signal is seen when you look not now in terms of nearest neighbour, but this sort of clustering metric, which is essentially you take a certain lag and you measure the number of pairs, like of real cloud to real cloud pairs that you have in that lag compared to random versus real and random versus random, which gives you this sort of clustering amplitude. And again, you can see that out to sort of a few hundred parsecs, the real distributions of GMCs are more clustered than you would just expect from an exponential distribution. So this, Josh has tried to look at whether we see some trend in these sort of clustering metrics in terms of galaxy properties. The main thing to see in those plots is that your early type, we do have a few early types in our sample despite our selection criteria. They're the black points, and the sort of very late types, which are these sort of lower mass, lower metallicity systems, are in yellow. And so that's sort of an example of those two types of galaxies, the CO emission distribution in those two types of galaxies. So essentially, apart from the fact that you can see very well that early types, all of the CO is right in the middle, so they seem to be highly. And in the late types, you have this much more sparsely distributed GMCs. Most of these normal galaxies, which is sort of orange and purple, actually essentially sit at a character spacings of 300 parsecs. Now, my view is that you shouldn't go away and think characteristic spacings of GMCs is 300 parsecs, because that's twice the resolution of the homogenized data that we use to make these measurements. But at least we can say is that that these type of structures have a spacing of at least 300 parsecs in our galaxy. I think if you observe with high sensitivity and high resolution, you'd get a slightly different number. Okay, and you don't see that there's an enormously strong trend, at least with our resolution sensitivity, on either stellar mass or CO luminosity. There's a few other galaxy properties, but none of these galaxy properties seem to make a strong prediction or a strong sensitivity to the characteristic clustering of GMCs. All right. So what about the properties of the clouds themselves? So the conventional view maybe in sort of mid-2000s when I was studying at my PhD, is that GMCs are strongly self-gravitating, they're decoupled from their environment. Doesn't matter which galaxy you look in, they all have the same surface density, similar mass, same sort of line width. You know, essentially these sort of universal objects, and the real mystery was like, where does the turbulence come from, such that they managed to stay up. So with PHANGS, we're able to sort of test this idea of universality because we have a much wider range of environments to look at, and also the luxury with so much data to actually try and homogenize the data properly. Quite a different thing to when you have 20 clouds as opposed to when you have tens of thousands of clouds, as to how the things that you can throw away essentially. So this was the first look that Eric Rosolowski did a year ago now. So this is the sort of the real parameter of clouds, their characteristic line width, so that their line width divided by their size, their surface density, and each of the distributions you see the different galaxies that was published in that paper. And this was sort of after he'd homogenized the data so the structures were identified at a fixed resolution and a fixed sensitivity. And so, you can see that indeed that these things have similar surface densities and similar line widths. And M sort of in this sample of 10, M64 sort of stands out as being a bit weird, high surface density and high line width. And then, but you have to keep in mind that a lot of the places that the galaxies we've chosen, are chosen to be quite similar as well. So once we had sort of more of the data delivered, he's a postdoc now, but he was a grad student at the time, JWST. He looked at, really took a close look at whether the properties of the GMCs systematically vary with properties of the host galaxy, either integrated properties like stellar mass, star formation rate, the whole galaxy, or sort of local kiloparsec scale regions within galaxies. Because within any one galaxy, you have high surface density regions and low surface density regions, but that mix of environments is not the same. So here, this is now looking for 60, nearly 66 galaxies, and so you can see the sort of the general trend between stellar mass and star formation rate in the background. So that's sort of, I think it's a Z0 MGS sample, and the color of the points is actually the mass-weighted median surface density of the cloud population in each of those galaxies. So as you sort of go to sort of more purpley colors, it means that the GMCs are getting more denser, essentially. And the change in the symbol is just because in these sort of low mass systems, our flux recovery into clouds is not as good as for the high mass system. So you can see that there is, in fact, a systematic variation in the surface density of clouds as you go up in stellar mass and star formation rate, which is sort of an order of 2 orders of magnitude across the galaxy properties that we probe in our sample. And so that's just now in terms of the global properties of galaxies, but it's a bit hard to actually see like what's the physical mechanism that a GMC says, oh, I know I'm in a 10 to the 10 stellar mass galaxy. So somehow the local galactic environment is the kiloparsec scale environment of the cloud is sort of mediating this relationship. And so now when you look sort of at regions within galaxies rather than global galaxy properties, this is again J.U. who did this. So this is now looking at their surface density versus their velocity dispersion, where he's color-coded the points by whether it's sort of gas in the disk, so just outside of the center, gas in the center of a barred galaxy, and then the contour is gas in the center of a galaxy but without a bar. And on the right, it's the subsample of galaxies where we really have strong spiral arm features, and at sort of and at the same galactic centric radius, what's the sort of typical surface density of a cloud that's in an arm or outside an arm? And there is, the dispersion is large. That's certainly true, but there is a clear systematic difference between these different environments. And this, you don't have to memorize this, but basically, sorry, my pointer's run out. But basically, on the left, the columns are sort of local kiloparsec scale environment properties. And on the right of the table, it's sort of global galaxy properties. And what you're meant to take away from it is that, you see much more dark red, which is a sign of a strong positive correlation when you really consider the kiloparsec scale quantity rather than a global galaxy property. And the inference is there that indeed we see correlations with stellar mass, but we see those because high stellar mass galaxies also tend to have higher stellar surface densities, and it's the stellar surface density, in fact, that's directly responsible for the regulation of the GMC properties. So that Jai has just submitted this paper, and essentially, the conclusion is that when you really look at these correlations in detail, it's a kiloparsec scale environment that shows the clearest trends with the changes in the GMC properties, and that the sort of the galaxy-to-galaxy overall correlation in the scatter is due to the fact that within any particular one galaxy, you have high density regions or low density regions. All right. So you might ask yourself, okay, so what's the physical model that we could try and use to explain some of these variations? So in terms of what we observe, I think the main sort of diagnostic plot for GMCs is their surface density versus their velocity dispersion, because for a virialized cloud, you'd essentially, or self-gravitating cloud, you'd expect them to lie along these diagonal lines in that perimeter space. And then the sort of internal turbulent pressure of clouds, which is the product of the velocity dispersion and the surface density, then sort of is orthogonal to that diagonal line. This is, since 2009, people have called this the Mark Higher plot, because we made a similar plot like this in the Milky Way. So this is both PHANGS data. This is sort of the updated version where we have the whole sample in, where the color coding is by the location in the galaxy. Yellow is centers and darker colors are sort of outskirts of galaxies. And this is just an earlier subsample of the PHANGS data, and which Jay included some of the local group dwarfs and also the antennae galaxy. So basically you see that GMCs, they sort of adjust their properties such that they end up basically lying around this sort of line of approximate equilibrium, which means that GMCs, they don't have uniform properties, so they're not universal. They actually cover sort of a couple of orders of magnitude in terms of their surface densities, and a bit less than that in terms of their velocity dispersions. But those properties sort of co-adjust such that they span a large range of internal pressures, but a much narrower range of dynamical states. And so how could that happen? So an idea that has been in literature since the 80s, probably before, but the 80s was sort of when I started looking into this problem, is that the internal pressure of clouds, which sort of depends on their density and turbulence, should be in rough equilibrium with the pressure of the surrounding medium. And that intuitively makes sense, because if they were significantly overpressured, then they would, they would disrupt, and if they were significantly underpressured, then they'd collapse. So in order to see them, they have to be roughly in that sort of regime. And so Jai has tested this much more rigorously than we were ever able to do with previous data sets. So each of the points in these plots now, what I'm plotting is an estimate for the kiloparsec scale dynamical equilibrium pressure at the midplane. And on the y-axis, it's the internal turbulent pressure, not of a single cloud. It's because you can only measure the dynamical equilibrium pressure on sort of kiloparsec scales. So on the y-axis, in fact, what we do is we take a population of clouds within a kiloparsec scale element, and then we sort of take the ensemble averaged turbulent pressure of that cloud. And then on the sort of bottom panel, it's essentially just taking that as a ratio, where if clouds were really just in pressure equilibrium, then they would lie along that red line. So while we see in that they do track each other, they don't. The clouds using this estimate for the dynamic equilibrium pressure at the midplane seem to be still overpressured. Yeah. So So of course, clouds, they don't just feel the pressure of the ambient medium, they also feel their own self-gravity. So the difference here is now that JE actually added a term that's related to the self-gravity of the cloud. So it has the ambient ISM pressure, but then some additional, a term that's due to the fact that clouds are, are dense and they have a weight. And so this is now this sort of ambient pressure plus cloud weight on the x-axis versus their internal pressure, and you sort of recover the relationship that you expect, that essentially these are things in rough pressure equilibrium. And then on the bottom, that's just showing the importance of this weight of the cloud term versus the weight of the ambient term. And essentially in about half, for about half of our sight lines, it's self-gravity that dominates the physics of clouds, which is sort of reassuring because that's what people always said. And so if we'd found that it was not that at all, then we'd wonder what was going on in the local universe, in the local group galaxies. But essentially what we expect from that is that, roughly half of the clouds in our sample, their lifetime is dictated by their self-gravity and their evolutionary processes. But, for the other half, they're in regions of, where their weight is not completely dominant over the external pressure, that the external pressure has more of a say in what happens to that cloud in terms of how it gets sheet apart or what its future will be. Okay, how about I go for time? Is this correct? Right there?
Yes.
Okay. All right, I won't speed up, I'll just leave some things out. So the next question, of course, is, okay, I'm a geek and I love molecular gas, and I could just talk about molecular gas all day without even talking about star formation, but most people care about star formation. So I'm going to show a few results about star formation. So coming back to the sort of general distribution of where star formation is happening in galaxies, it's exactly the same plot on the two left-hand columns as I showed before. And on the right now, as I'm just showing, taking sort of a fairly standard star formation rate map based on UV and infrared bands, like where now is the star formation happening within these masks. And what you can see is that, again, centers are more highly performing in terms of star formation rate, even compared to their molecular gas mass, let alone their area. And for most of the other environments, in fact, this notion that the ratio between the molecular gas and the star formation rate is just about the same, which is sort of what we see on galaxy scales as well, but it seems to hold on these large-scale galactic environments, except in centers. But the differences actually were sort of, even for the center, were, I think, smaller than what we expected, in the sense that, once you actually once you express this as a depletion time, which is literally just the amount of mass divided by the star formation rate, the sort of characteristic depletion time in the centers is a bit lower than the other environments, but it's not radically different. That's a divergence, and I don't have time. So it's a bit of a shame with that high resolution data to have just done these big categories. So another piece of work that I did with Eva Shinera was to say, okay, once we have these maps, like, can we just map out where the CO is, where the H alpha is, and where these two things are coincident in space? Because the sort of mid-2000 Kennecott-Schmidt law would have told you that wherever you see molecular gas, you're going to see star formation, right? Is that true? So that's essentially our input data sets. They were sort of the ALMA CO, some narrowband H alpha, which was literature at the time, and then the sort of output of this analysis, it's too simple to be called analysis, was these sort of masks where blue means this is the regions of galaxies where I only see CO, red is where I only see H alpha, and pink is where I see both the CO and the H alpha traced together. And our idea was, firstly to just measure these fractions at the best resolution possible, but also to see, like, what happens if you change the resolution of your data? Like, could you recover the sort of kilopascal scale result by, like, making the same comparison after degrading the resolution of the galaxies? So the key results from this sort of pilot study, which only had sort of 8 galaxies was that indeed at the sort of 100 parsec scale resolution, these blue regions, which is the CO only pixels in these galaxies, for many of the galaxies, not all, but for many, there are significant, there's this significant fraction of CO gas that doesn't have a finite high mass star formation as traced by H alpha. But, you don't have to go degrade the resolution very much. You don't have to go to sort of 500 parsecs. And these things are obviously close to each other, such that once you're at 500 parsec resolution, you have the impression that there's just every time you see CO, there's high mass star formation. And one of our postdocs, Sian, once we had the full sample of PHANGS ALMA observations and we had new narrowband H alpha imaging, she redid the same work, but for now 50 galaxies. And the main result from this study was that sort of, at that 150 parsec resolution, that fraction of the CO gas that's overlapping with star formation is remarkably constant. So these different bars are the stellar mass of the galaxy, and the y-axis here is the fraction of the sight lines that have both CO and H alpha in yellow, H alpha only in red, and CO only in blue. And so you can see that as you go from low mass to high mass galaxies, that percentage of CO with star formation is roughly constant. But on the other hand, as you go to high mass galaxies, the amount of CO that you have without star formation is going up, and the amount of H alpha you have that is not overlapping with molecular gas is going down. So we had hoped, I think, that this would have some relationship to how far our galaxies were on or off this main sequence. So on the x-axis here, I'm plotting the offset from that star forming main sequence trend line. And so galaxies sort of to the right of one star from galaxies that are forming more stars than you'd expect based on their stellar mass. And on the left, it's sort of galaxies that are not forming as much stars as you'd expect relative to the main sequence. But yeah, we didn't really see any clear trend. And it's just, yeah, that was a bit disappointing actually. But on the other hand, we selected galaxies to lie in the main sequence. So it would be interesting to know what happens if you sort of had a selection of galaxies that really got well off the main sequence in terms of these properties. Okay, so just to conclude, I wanted to talk briefly about work that some of the group has done about trying to measure the timescales of star formation and feedback. So this is an idea that was put in the literature by Diedrich Claassen, going back to 2014 now. And basically the idea is, you have a spatial distribution of gas and star formation traces. And if a trace that lives for a long time, then it should be common. And if a certain phase of the star formation cycle that's traced by a certain trace that is short, then it will be less common. And so with their conceptual framework, what that allows them to do is, you have sort of a galactic average of the CO to H alpha ratio, if we're using CH and alpha. And then if you have apertures of increasing size, and you measure that ratio, so this is increasing cloud scale from left to right on the right-hand plot. So sort of going out each time in terms of the amount of the galaxy surface that you're covering. And so for something that exists for a long time, you won't get very far off the galactic average, because even if you have even if your aperture doesn't increase that much, you'll quickly incorporate a lot of the flux from that tracer. But on the other hand, if you have a very short time scale, then you have to sort of increase the aperture a lot before you sort of start hitting another one of those traces and adjusting the flux ratio. So that's the sort of conceptual no mass way that this framework works. And so essentially it's from fitting these sort of bias curves around the galactic average of your gas only or your star formation tracer that you sort of manage to back out a a timescale or a relative timescale. And then if you have something that gives you an actual absolute timescale, which in our case is the sort of the typical lifetime of an H2 region based on models, you can turn those ratios into an actual mega years, basically. So this was a paper that Melanie Schwartz did using sort of 9 of our first galaxies. And essentially the bars here you can see are the relative form. The orange is the time for which the sort of GMC or the clouds exist without sort of high mass star formation. The red is where you have coexistence of the H alpha and the CO, and then the purple, which is by definition the same in all of the galaxies, or nearly the same, is the lifetime of an H2 region. So the conclusion there was that, you know, when I was doing my PhD, there was a debate as to whether molecular clouds lived a few mega years or hundreds of mega years. Certainly what we see from PHANGS with this sort of conceptual framework is that, you know, the cloud lifetimes are much more like 10 to tens of mega years, but they're not hundreds of mega years, essentially. And the other thing is that this feedback phase is short, even compared to that short cloud lifetime. So I'm aware that we're going to be running out of time, but essentially I'll let you read the paper to get the details. But Melanie compared some of the sort of timescales that are associated with the internal dynamics of GMCs, their free fall time or their crossing time, with a model for sort of galactic scale processes that you might think would affect GMC evolution, like shear and cloud-cloud collisions. It's a model that's described in Sarah Jefferson's paper. It's environment dependent, but it takes account of 4 or 5 different effects, galactic dynamic type effects that could affect magnetic clouds. And in general, the conclusion that Melanie drew was, and that's based on the relative position of the data points, which are the black points, compared to the galactic dynamic model, which is blue, versus the sort of internal dynamics of clouds estimates for timescales, which are in red. It was particularly in sort of low density regions of galaxies. It's really the internal dynamics of clouds that determine their survival. But as you get to higher densities, then these galactic scale processes, which, you know, have shorter and shorter characteristic timescales, can also become competitive with the timescales of internal processes. This is a separate paper, but it uses exactly the same set of analysis. It's now just taking a closer look at the feedback time, which, as I mentioned before, is quite short. And here, the blue lines now are different feedback processes and a characteristic timescale for the different feedback. So the ones that Melanie considered were stellar winds, radiation pressure, supernovae, and photoionization. And the key thing to take away is just that the supernovae and the radiation pressure, I only showed 3 of the galaxies here, but in general, the timescales for those processes are sort of quite a bit longer than what we estimate from data to see the feedback timescale, which suggests that sort of pre-supernova feedback mechanisms like stellar winds and photoionization seem to actually be quite important for disrupting clouds in the types of environments that we probe with PHANGS. And this is just an update of that same result, but now done by Melanie's PhD student, Jia-Yun. So essentially, she's applied exactly the same analysis framework, but now we have 55 galaxies, and so she's essentially confirmed the results from the pilot study that the typical lifetime of GMCs are sort of 10 to 20 mega years, and feedback timescales are sort of 1 to 5 mega years. Okay. So unfortunately, I didn't have time to talk about everything that everybody in the collaboration has done, but maybe if the slides are put somewhere, I would recommend going and seeing all the other fantastic work, especially in the MUSE and the HFT parts of the survey that I haven't talked about at all today. Please do use the data. That will make me feel much, much better about the fact that I haven't actually done very much research in the last 5 years because I've been so busy trying to get these products out. So yeah, we we put them into the public so that everybody can use them, and we really encourage you to go and download both the images, the cubes, the catalogs, the software, everything you can, and all of it is linked from our main project webpage. That's just to quickly remind you that you know, everything I've talked about today is a huge effort from a big team, and so all of these people deserve credit for the results that I've talked about today. And so this is my summary. Basically, we're aiming to build a legacy astronomical data set across you know, a multi-wavelength data set, which can allow us to chart the cycling between young stars and cold gas in environments that are representative of star formation and the nearby galaxy population. I think we've now clearly established that molecular gas properties do depend on the properties of the host galactic disk. They're not sort of universal billiard balls floating in space. And that sort of centers of galaxies do seem to, of barred galaxies do seem to exhibit some sort of unique features. In terms of the timescales of star formation and feedback, everything we've done so far to date suggests that, you know, that these timescales are rapid. And yeah, as I said before, you know, we've now finished the ALMA, the MUSE, and the JWST surveys. We've done data releases for all of them, at least first data releases. So please do use the data product.
I think I take the question from the room, and then we will check the chat and hopefully
Yep.
I don't know with which instrument, okay, but for sure, considering the same resolution as before, when you have the ratio.
Yes, yeah.
Then, how you take into account the obscure star formation? You correct the
No.
no.
Not at all. So yeah, that's, yeah, so when I say, I don't know if you, when I say star formation free gas, of course I'm being lazy, because there could be the star formation that's still embedded. That's one of the drivers to observe these same galaxies with JWST to work out, you know, because you're quite right, like it could be CO that's truly inert, it could be CO forming that are forming low mass stars, preferentially forming low mass stars such that we don't see it. But yeah, in terms of the actual analysis we did, we just didn't take into account at all. No, not at all. That said, there's Jia-Yun Kim. I showed her result right at the very end with 50 galaxies. She has another paper where she does take it into account using the 24 micron list. Yeah, but for a smaller sample of galaxies. But it, I don't want to say something stupid. It doesn't completely make this star formation free CO phase go away. You know, of course, you see this star formation lights up in the embedded phase before, but there's still on the sort of life cycle of a GMC, the CO only phase with the 20, you know, tracing embedded with 24 micron, you know, with the sensitivity of the 24 micron that we have, it's still, it doesn't, you know, it doesn't eat up all of that CO only. Okay. Yeah, thanks.
yeah, I don't know if that's okay.
No questions in the chat or
Thanks for a wonderful talk. Very nice also to have talks. Real nice. I wanted to ask, did you see the difference between spiral galaxies with bars and spiral galaxies without bars? Does the bar somehow enhance the spiral arms or allow more concentration of star formation along them, or?
So when you say difference, you mean for galaxies that have a bar and spiral arms,
Yeah.
if they have a bar,
Yeah.
do we see changes in the star formation efficiency of the arms?
Yeah, or the distribution.
Well, in general, I don't have the final answer, sorry, because we have 28 galaxies that have really clear spiral structure, you know, like, you know, where you can trace out the beautiful. So it's not hundreds of galaxies to make tests. And then of them, I think, some fraction of them have bars, but not all of them. So we're still in the low statistic regime. What we see in general with the spiral arms is that we don't see a change in the star formation efficiency. I think PHANGS in general confirms the picture that the arms are very good at gathering gas and star formation together, but they don't change the efficiency with which that's without the consideration of bars. I don't think anybody has specifically, we've looked at the centers of barred versus unbarred galaxies, but I don't think anybody specifically looked at spiral, star formation efficiency in the spiral arms of galaxies that also have bars. Is there a particular physical mechanism that you would expect that would change that?
We see also in our data in the Milky Way that we have star formation in the arms and out the arms, but if you look for specific risk behind a star formation, typically arrives on the arms, while if you look at star formation in a more general way, in the infrared, then you can see that the whole galaxy lights up.
Yeah. So
it's difficult also.
Go back to, certainly, so certainly when Melanie and Jayun, pardon, they had to be very careful with bar ends. So not this is just the ends of bars seem to be regions of galaxies where the hypotheses that they use for this separation tuning fork thing break down. So I have to admit that the cyan points there don't look that different to the black points, but we certainly, like in the Milky Way, we see bar ends as being like amazing stars of formation. No. So, sorry. Yeah. So that not across the whole survey. So we have some galaxies. There has been some additional observing to look at the 90 gigahertz sort of species. And then when we started, the 13 CO 2:1 was not observable simultaneously with the 12 CO 2:1. Yeah, and so since then, so the bulk of the galaxy, the bulk of the survey was done without 13 CO. We've had a few targets that we've added as time's gone on, and in those cases we've added 13 CO, but we haven't done a systematic, and it's not nearly the number of galaxies that we talk about here. Yeah.
First, I'm using ALMA PHANGS data, so
thank you.
It's very useful for me. Thanks for the and I have two curiosities. The first, showing a plot with the different properties of cloud for all sample galaxies.
Yeah.
There is a galaxy, maybe NGC.
M83
with a property with a shifted in each plot in blue.
It was the median properties of
with the line with
this one. That's M64. Yeah, 4628 or 4826. Yeah.
Okay, and it's peculiar. This galaxy, do you remember why this galaxy is shifted with respect to other galaxy?
I have to admit, I'm not a super expert on all these individual galaxies. It's M64, which is also known as the black eye or the black hole. No, not the black hole, the black eye galaxy, the evil eye galaxy, or something like that. Yeah, I'll have to go and have a look to see. But you're right that in particular, the fact that the line width and the surface density are high, and why not? But what is a bit strange is that the urial parameter is also right. Yeah.
And then another curiosity, very similar to the question done by Kasi, that the amount of data available with PHANGS is very great, okay? And focused on, for ALMA, on CO2 emission line. Do you plan to perform a similar survey at high J? So to trace in homogeneous way, okay, dense gas.
We have tried. So very hard to. CO2:1 at this resolution is just the most so super efficient.
Okay.
Like this is already hundreds of hours. If you go to higher J and you want the same as, what we have tried, and this is probably, I hope nobody's on the tack, is we have tried getting 3 to 2 systematically, but the strategy would be to take it slightly, take a bit of a resolution hit and go down to sort of a few hundred parsec resolution. And that's such that you could observe 1 to 0 with the ACA and 3 to 2, no, 3 to 2 with the ACA, and then 1 to 0. You see what I mean? So that it's not high J.
Okay.
But, because otherwise, yeah, high J and lines like HCN, it's really only specific regions and specific targets that we've tried to do so far. I think maybe 2903, maybe 1 or 2 galaxies we've tried to do like mapping across the disk, but for 1 or 2 targets, not 20.
Okay.
Yeah.
There are no
Have to do it with super armor.
No other questions from you?
Maybe there is a last
Yes.
Yeah.
I see that in our sample cut, there are some single galaxies.
Okay.
I was curious if you could see an effect from the AGN in the CO emission. Someone in the group has done.
So I certainly haven't. I will have to. So I think Sophia Stuber, who's a PhD student at MPIA, may be starting to look. I'm not sure she's looking at CFITs in particular, but I know that she's been looking at the centers of galaxies and looking sort of in a relationship with AGN and the outflows. So I could ask Sophia if she can give you a better answer. Yeah.
Okay, I think Jenny has to run. But there are no other questions from outside, not from the room. And Annie she's still here in the afternoon, so if you need to talk to her, is at the 4th floor at the Institut of Recherche.
Yeah, so Viviana does it.
So thank you everybody from outside, and thank you, Annie.